So question in the back was, is there some way to filter out the non-real solutions? And the answer is that SymPy expressions have a dot is real attribute on them, which tells you if the expression is real or not. So for example, 1 or SymPy of 1 dot is real is true, and SymPy of, I just do I, is that going to work out? So I think the imaginary SymPy variable is I, and that's not real. And so what I tried to do to solve your problem was to do list comprehension around the solutions, asking if SymPy could infer that that solution was real, and it gave me none of them back, which it was perplexing. So it successfully told me that these ones were not real. But the first one, we sort of hoped it could infer that it was a real number, that this was real. And so Aaron suggested that maybe it can't figure out that v to the power of 1/3 is a real number if v is a real number. So that's where it's failing. Sure. So you're suggesting that we could put in here that v is a positive number.
It's the classic negative 1 to the 1/3. Gotcha. In computing, numerical computing.
Yeah, the classic numeric. Yeah, everyone's familiar with that classic.
It's not specific to SymPy. It's because if you take the cube root of -1, it doesn't give you -1. It gives you.
Okay. Yeah. So you're right that if it was positive, we're fine. The cube root of -1
it gives you a complex number.
Is a complex number, and so if
the first principal root.
So there's all those this is all the roots of -1. Yeah. So here we can add them extra information. We can tell SymPy that, hey, v is positive as well as v is real. And then we print out here, and it's able to infer that v is real, that this expression is real. And so when we do this, hopefully we get out our one real solution. Yeah. Let's move past that. So is real is part of our assumption system. That lets us, you can specify certain things about your expressions. You can ask other questions about your expressions. I'm not going to go into that because that's sort of more complex than I wanted to go into right here. But for the short term, we can also just grab out the first solution, which is, for the short term, what I suggest. Okay, so this was the solution to a previous exercise. Now that we've solved this for R, okay, so given the volume of a sphere, this is the radius of that sphere. And we can look at it, it sort of scales as we expect. As the volume increases by a factor of 1,000, the radius increases by a factor of 1,000, the cube root increases by a factor of 10. Okay, so that same cubic relationship, we're just now seeing it in reverse. Okay. And again, solve is able to give you these solutions. Okay. So now let's compute the surface area of a sphere. So maybe surface area equals something up here. And then substitute in surface area and replace the r's by v's. And we'll now see how the surface area scales as the volume increases. Okay, so exercise, write down the surface area in terms of r, and then take that surface area expression and substitute in r for our solution up here. So we're going to rewrite surface area in terms of volume. Right. So if you don't even want to write down this surface area thing, you can just take the derivative of the volume with respect to radius. Right, because its shell is increasing outwards. Yeah. Clever. People who actually know math. Sorry? Okay. People able to do that? People satisfied? So what is the surface area scale like in terms of the volume? Does it scale in a way that seems reasonable to you? So I'll do it up here. The subs in R for the solution. So we can define the surface area. I use his clever trick of taking the derivative of the volume. I then substituted in for that surface area R for our solution. So remember we had solved the volume in terms of the radius. So we're taking that same solution that mapped radius to volume, and we're plugging it into surface area, and we're finding that the surface area scales as the volume to the 2/3 power. So that again, like matches intuition, sort of makes some sense. So again, we're using solve, we're using subs. We can use them together to do some nice math. So SymPy has a plotting story. Generally speaking, like the plotting ecosystem in Python is blowing up right now. You should use one of their projects. SymPy has some internal plotting mechanism, which plugs into various other backends. We default to matplotlib. Here we're plotting x squared. There's a little bit of fancy logic to figure out, how big should we make our ranges. We set up more information than these plotting libraries have because we don't have just a bag of numbers. We've got much more information in the symbolic form. So exercise, use the plot function to plot the last relationship we just had. So you did this. So plot this using plot. If you want to be extra explicit in plot, you can say the variable with which you want to plot against. Oh, how do I do this? No, it's giving me two plots.
Oh, maybe you put it. I don't know, maybe you just put it.
Yeah.
This is like.
For univariate plotting, just.
Variable and but like the next part is like a tuple variable.
Okay, I'm not going to worry about it.
You don't need to put the variable in because you can only plot one variable.
This is the surface area in terms of B. So we can plot a relation, the volume in terms of surface area. And then just for fun, so again, SymPy, we try not to build our own systems. We try to hook out to other systems. Here's an example of using some other plotting system. This is my favorite of plotting libraries. It's you've heard of, Seaborn, and there's Bokeh, there's Matplotlib, there's D3. Even fancier is TextPlot. Right? I really like TextPlot. So here's TextPlot. Does an ASCII plot. For those of you in low-tech situations, you can plot out things in a nice way. This is actually a good place to note that SymPy is sort of the easiest compute auto system to install and run. The dependencies are it's a broad claim, but it's a very easy and accessible compute auto system. We've got lots of users around the world. We try to sort of maintain those users. So things like text plotting are actually maybe sometimes useful. Okay. So that's it. That section. Let's take like a 10-minute break. Is this a good break time? So I'm getting a thumbs up. So there's a scheduled 20-minute break at the 2-hour mark. Do you want to take that now, or do you want to take that later? Whoever expresses an opinion right now has their opinion rule the... Let's take a 10-minute break. Go out and do some stuff. We'll take another 10-minute break later. Let's come back at 2:45.